In this problem, we will solve the for the displacements of the joint of a truss. So this is the truss given. We need to find the displacement components at joint B. So this is the free body diagram for the joint B. The forces in the bars will be along the length of the bar because the bars will be in axial loading. Then from the equilibrium of horizontal forces, the sum of horizontal forces should be 0. So FBA cos 60 should be equal to FBC cos 60. This gives rise to FBA is equal to FBC. Similarly, if you take the vertical equilibrium, you get FBA sin 60 plus FBC sin 60 plus 600 is equal to 0. In other words, FBA will be minus 600 by root 3 kilonewtons. Same value will be for FBC also. Now if you take the elongation of member BA, it will be given by PL by AE, force in the member AB, length of member AB, area of member AB, Young's modulus of member AB. So it will be these values here, 600,000 divided by root 3 newtons into 2400 mm by 1000 mm square and 110 Newton per mm square of E value. So it gives delta BA of 7.56. Then similarly we can calculate the elongation of the member BC. After getting these elongations, we need to find out the resultant displacement. Since the bars are like this, the bar AB is subjected to axial compression. Let us say A is the compression or the shortening of the bar AB, and it will have its components in the horizontal and vertical directions, that is in X and Y directions, A cos alpha and A sin alpha. Similarly, you have the shortening of bar BC, and let us say B is the shortening of bar BC. It will have its components B cos beta and B sin beta, like this. Now the final point will lie on a perpendicular to the bar AB and also a perpendicular to bar BC. Okay, from this point if you draw a perpendicular, so the final position of the point B will be somewhere here. So if you resolve it into components, because this angle is alpha, the components will be X cos alpha in the vertical direction, X sin alpha in the horizontal direction. Similarly, the final point will lie on this normal from member BC, this blue colored normal. Let us say that distance is y. So then the components will be y cos beta in the vertical direction, y sin beta in the horizontal direction. If you see from the geometry, we can conclude that the sum of this A cos alpha plus B cos beta, this sum should be equal to X sin alpha plus Y sin beta. So that is what is written in the first equation. Similarly, in the Y direction, A sin alpha plus X cos alpha should be equal to B sin beta plus Y cos beta. So that is written in the second equation. This is the geometric condition required. So if we rearrange the terms, all the X terms and Y terms will take it on to the right hand side. So first equation remains as it is. In the second equation, X cos alpha term will go to the right hand side. So you get this equation. On solving this, since we know A, B, alpha, beta are known to us, we can find out X and Y from these two equations. Then we can, the delta Bx is the horizontal displacement of this point. So starting from this point to this point, the horizontal distance is b cos beta minus y sin beta, and the vertical distance of this point from the original point B is a sin alpha plus x cos alpha. So using these expressions, now in this present problem, we know the value of A, the shortening of member AB is 7.56 mm, the shortening of member BC is 10.39 mm, the angle alpha and beta are equal to 60 degrees. So if we substitute, the LHS will be 8.975 in the equation 1. The LHS for equation 2 is minus 2.451. So when we solve it for x and y, if you solve these two equations simultaneously, you get x is equal to 7.633 mm and y is equal to 2.731 mm. So again, if we have to find out the horizontal displacement of point B, that means how much the point B has moved from its original position in the horizontal direction. So you have to write in this b cos beta minus y sin beta, which is 2.83 mm, and the vertical displacement will be 10.36 mm, which are the correct answers.